Hi, this is Chris. Now that we've added rounding to the floating point multiply circuit, it's time to look at how to do addition. I'm going to start with a review of how we add integer numbers. To begin, the simplest case is adding 0 to another integer. When adding 0 plus any number, say x, the sum will always be x. Because addition is commutative, when we add x plus 0, again the sum will be x. Next, consider adding two positive integers. This is just ordinary addition as we learned it in elementary school. So, for example, 3 plus 5 equals 8. What about adding two negative numbers? This is similar. If both numbers are negative, we first do the addition acting like the numbers are positive. Then we apply a negative sign. So to add negative 3 plus negative 2, we start by adding 3 plus 2, which is 5. Then we add the negative sign, so our final result is negative 5. When adding a positive number and a negative number, things get a bit more complicated. Say we want to add positive 2 plus negative 3. Instead of treating this as addition, we treat this as subtraction of two positive numbers. We start by subtracting 3 minus 2 to get 1. Then, because the magnitude of negative 3 is greater than the magnitude of positive 2, we add the negative sign to get a result of negative 1. Similarly, to add positive 5 plus negative 3, we subtract 5 minus 3 to get 2. And because the sign of the number with the larger magnitude is positive, that is because the absolute value of positive 5 is greater than the absolute value of negative 3, we add a plus sign to get positive 2. Now let's look at adding two binary floating point numbers. To keep things simple, as usual, I'll assume we're using the binary 16 format. Let's add 2 plus 1. Writing this in binary, we get 1 point followed by 10 zeros times 2 to the first power, plus 1 point followed by 10 zeros times 2 to the 0th power. We can't yet perform the addition because the exponents for the Augend and the Addend are different. We need to adjust the exponent of the smaller number so that it matches the exponent of the larger number. That is, we need to increase the exponent 0 to 1. But that's not enough. Because we made the exponent larger, we need to make the mantissa smaller by shifting it one place to the right. So our floating point representation for the number 1 becomes 0.1 followed by 10 zeros times 2 to the first power. Now we can add the two mantissas to get a new mantissa of 1.1 followed by 9 zeros. Appending the exponent term, our final result is 1.1 followed by 9 zeros times 2 to the first power. Adding two negative floating point numbers is similar to adding two negative integers. We treat the numbers as if they're both positive, perform the addition, and then tack on the negative sign at the end. Adding a positive floating point number to a negative floating point number is also analogous to the procedure for adding a positive integer and a negative integer. Subtract the number with the smaller magnitude from the number with the larger magnitude, and apply the sign of the number with the larger magnitude to the difference. When developing the multiply circuit, if one or both of the operands was a NaN, infinity, or 0, no actual multiplication is done. Actual multiplication was only performed in the case that the two operands were normal or subnormal numbers. For normal and subnormal numbers, the FP class module extracts the 5-bit biased unsigned exponent and converts it to the actual 7-bit signed exponent. FP class also extracts the 10-bit significand field, adding the implied leading 1 bit for normal numbers. You'll recall that subnormal numbers have significands which are between 1 and 10 bits of precision. FP class pads out the subnormal significand to 11 bits to allow the same logic which multiplies normal numbers to work with subnormal numbers. The 7-bit signed exponent field returned by FP class can hold values between -64 and +63. When multiplying two normal or subnormal numbers, the exponent values can range from -48 to +31. So when we compute the product, adding the two exponents together, we will never overflow the 7-bit signed exponent field. Because the two significands are 11 bits each, we know that their product will always fit into a 22-bit field. While it's true that the final product is rounded, so that the exponent field is only 5 bits, and the significand is only 11 bits, the internal intermediate result is the exact product of the two normal or subnormal numbers. Any loss of precision only happens during the final rounding. Loss of precision is signaled by the exception vector. When allocating space in the FP add circuit, again, we can use a 7-bit signed exponent for the internal result. But how much space do we need to allocate for the intermediate significand sum? You should remember from earlier videos that the smallest possible subnormal number is 1 times 2 to the -24th power. If we allocate 24 bits to the right of the binary point, we should be able to hold the very smallest possible non-zero value. What about the largest magnitude? You should remember that the largest possible exponent for the binary 16 format is called Emax and has the value of 15. At a minimum, we need 16 bits to the left of the binary point to hold the largest possible significand. Remember that the digits to the left of the binary point are multiplied by powers of 2, ranging from 2 to the 0th power to 2 to the 15th power, which is a total of 16 digits. But what happens if we add two numbers which both have an exponent of Emax? We will get a carryout, so we need a 17th bit to hold that carryout. We still need one more bit. For reasons which will be explained later, the extra bit is needed to hold a sign bit. Using the information we have so far, we would need the following values to exactly compute the sum of two significands. However, we shouldn't be using magic numbers. By using symbolic names for the numbers, we partially document how the values were derived and make the code reusable for other binary floating point formats. For the binary 16 format, this requires 42 bits of space for each of the significands for the Augend, Addend, and the sum. So let's start writing the code for the floating point addition circuit. As before, we'll start with the special cases. If one or both of the operands is a signaling NaN, we need to return a signaling NaN. We also need to raise the invalid exception. If neither operand is a signaling NaN, and one or both of the operands is a quiet NaN, we return a quiet NaN. The next case is if one or both of the operands are 0. Per section 6.3 of the IEEE 754 specification, when x is 0, x plus x or x minus negative x have the sign of x. The next special case is when both of the operands are infinite. If the signs of the two infinities are different, we need to signal an invalid exception and return a quiet NaN. If the rounding attribute is round ties to away, then we return the appropriate signed infinity value. For round towards 0, we return plus or minus the largest finite number. For round toward positive, we return either positive infinity or the most negative finite number. For round toward negative, we return either the most positive finite number or negative infinity. The following implements the logic for all of the various cases of adding two infinities. If one of the operands is infinite and the other is finite, we return the signed value of the infinite operand. Now the real work begins, adding two non-zero finite numbers. I'm going to take this in stages. First, I'm going to handle the cases where both numbers are positive or both numbers are negative. The steps for this are: adjust the exponent and significand of the number with the smaller absolute value. Add the significands. If there was a carryout of the most significant column, right-shift the sum of the significands and increment the larger exponent by 1. Apply the correct sign for the final sum, round the significand, and construct the binary 16 return result. Let's write the code. Test to see which exponent is larger. Make the larger number the Augend and the smaller number the Addend. Save the sign of the Augend. Save the exponent of the Augend. Compute how many bits right we need to shift the Addend to align the two significands. Right-shift the Addend. At this point, Control leaves the always block and passes to an instantiation of the p-adder42 module. This places the sum into sumsig. We test bit Emax plus 1 of sumsig to see if there was a carryout. Because we've allocated extra space for the significands, the carryout doesn't get reported by p-adder42 in the cout1 argument. If there was a carryout, we shift sumsig right 1 bit and increment sumexp to normalize the result. The updated significand and exponent values are saved into big sig and big exp respectively. The sign of the Augend, also known as sum sign, big exp, and big sig are passed into the rounding module. After rounding, Control passes back into the always block where we construct the binary 16 return value. I'm not going to dwell on the details of constructing the value since this was covered for the multiplication circuit. Obviously, this isn't the completed addition circuit. We haven't yet dealt with the case that the two operands have opposite signs. We need to do that now. We start off the same way. Test to see which exponent is larger. Make the larger number the Augend and the smaller number the Addend. Save the sign of the Augend. Save the exponent of the Augend. Compute how many bits right we need to shift the Addend to align the two significands. Right-shift the Addend. Here's where things are different. We can't just add the two significands. We need to perform a subtraction. When manipulating integers, addition and subtraction are effectively the same operation. This means we should still be able to use the p-adder42 module to subtract the significands rather than add them. To start, when we enter the always block, we save a flag which tells us whether the signs of the Augend and the Addend are different. We do this with the exclusive OR operator. To subtract the Addend significand from the Augend significand, we need to convert the Addend significand to its 2's complement form. As a reminder, we convert an integer to its 2's complement in 2 steps. Invert all the bits of the integer to get the 1's complement. Then add 1. Here is our original instantiation of the p-adder42 module. Here's how we convert Addend sig to its 1's complement value using the subtract flag. The next step, adding 1 to the 1's complement of Addend sig to get the 2's complement, can be done by using the subtract flag as the carry in bit. If necessary, pause the video and take a few moments to convince yourself that when the signs of the Augend and the Addend are the same, that the significands will be added. But when the signs of the Augend and Addend are different, the significands will be subtracted. Now we need to move on to deal with the side effect of subtracting the two significands because their signs are different. Let's look at adding 1 point followed by 10 zeros times 2 to the 11th power, and negative 1 point followed by 10 ones times 2 to the 10th power. Adding 1 to the exponent of the second number and shifting its significand one place to the right, we get negative 0 point followed by 11 ones times 2 to the 11th power. When we subtract the two significands, we get 0 point followed by 10 zeros followed by 1 times 2 to the 11th power. This time, instead of renormalizing by shifting the significand right and incrementing the exponent, we need to shift the significand left and decrease the exponent. In order to get the most significant 1 bit of the sum to the left of the binary point, we need to shift the significand left 11 places. Because we need to shift the significand left 11 places, we subtract 11 from the exponent. The final result is 1 point followed by 10 zeros times 2 to the 0th power. We saw how to perform this left shift before when we examined the HP class and FP class modules. Here I introduce two new values, normsig and normexp. Then using a for loop, I test for a string of 8 leading zeros. If 8 leading zeros exist, the code shifts normsig left 8 places and increments the count of how many places the significand was shifted. The loop then goes back to see if the significand has 4 leading 0 bits, and then 2 leading 0 bits, and finally 1 leading 0 bit. Again, there's nothing new here. However, we need to update the code to pass normsig and normexp into the rounding module instead of passing big sig and big exp. On to the next wrinkle. What happens if I add 1 point followed by 10 zeros times 2 to the 0th power and negative 1 point followed by 10 zeros times 2 to the 0th power? We of course get 0. I need a way to detect that all of the bits of the significand are 0. To do this, I add a new flag called 0 and initialize it to true. In the for loop, which strips off the leading zeros, if ever the leading 0 test fails, that is, if any of the bits in the significand are 1, then the 0 bit gets set to false. When constructing the return value, I first test to see if the 0 flag is true. If it is, then I construct the appropriate signed 0 value. What you see on the screen is code added to deal with the 0 case. There's one more special case. What happens if I add -2 plus +3? The floating point representation of -2 is -1 point followed by 10 zeros times 2 to the 1st power. And the floating point representation of 3 is 1.1 followed by 9 zeros times 2 to the 1st power. The exponents for both the Augend and Addend are 1. The if statement test AEXP less than BEXP will fail, so the code will go through the else clause and assign the significand for -2 to Augend sig and the significand for 3 to Addend sig. Because our two operands have different signs, the subtract flag will be 1, and p-adder will perform a subtraction. The result of the subtraction will be -1. We can see that the result is negative by testing bit sumsig emax plus 2, the mysterious, previously unexplained sign bit, which I added when I determined the size of the significands. Why did we get a negative result? The assumption was that the code makes the operand with the larger magnitude the Augend and the operand with the smaller magnitude the Addend. This did not happen in this case because the exponents are equal, and the else clause just assumes that when the exponents are equal, that the first operand is always bigger than the second operand. I'm going to fix the problem by taking the absolute value of sumsig and flipping the sign bit stored in sumsign. To take the absolute value of sumsig, I'm going to use another instantiation of p-adder42. The first operand passed into p-adder42 is the value 0. Then using the sign bit of sumsig, I'm going to conditionally compute the 2's complement of sumsig. If sumsig is positive or 0, then absig is equal to sumsig. If sumsig is negative, absig is the 2's complement of sumsig. In either case, absig equals the absolute value of sumsig. Now it's time for some study questions. Instead of computing the absolute value of some sig, why didn't I expand the test for Augend and Addend to see if when the exponents for the two operands are equal, which significand is larger? For the case when the two significands need to be subtracted, I added a for loop. I said that in the first pass through the loop, that the loop tests for 8 leading zeros, then 4 leading zeros, 2 leading zeros, and finally 1 leading zero. Technically, this isn't true. How many leading zeros does each pass really test for? And why is the count different? This implementation of the addition circuit calculates the exact value for the sum of the two input operands before rounding. Why is calculating the exact sum bad? The GitHub repository with the code for this video can be found in the comment section. The next video will cover creating the addition circuit with a more efficient use of resources. Please share this video with friends and colleagues who might have an interest in the video series. Questions and comments are welcome in the comments section. If you found this video useful, please click like below. While you're at it, subscribe to the channel, then click the bell to be notified when new videos are available. Thanks.